Hey, lovely ochemers. How's it going? All right, so last time we talked about stereogenic centers, and we discussed the fact that that would happen if you have, for example, something with an R or an S configuration. That would be a stereogenic center. And, but now we're going to talk briefly about them again. The maximum number of stereoisomers, so in other words, the amount of different configurations you can get with the different centers is 2 to the n. So if you have something like something with 2 stereo centers, so it would be 2 to the 2 equals 4, or something with 3 stereo centers, it would be 2 to the 3, right, which equals 2 times 2 times 2. This would be 4 times 2 would be 8 stereoisomers. So that's the amount of different compounds that you can actually get. So something with 5 stereogenic centers would be 2 to the 5, right, which would equal 2 times 2 times 2 times 2 times 2. And you can put it in your calculator, or we can do it here. This would be 4, that's 8, that's 16, and that would be 32. So there'd be 32 different possible compounds that you could get different isomers for that one single compound with 5 stereogenic centers. All right, let's go ahead and look at this one. So it says label the 2 stereogenic centers and draw all possible stereoisomers. Okay, so here, remember, a stereogenic center is something that has a carbon with 4 different things on it. So I see this one right here. The 4 different things, we have this ethyl stuff, we have this thing over here with an alcohol, we have this chlorine, and then we have a hydrogen, which isn't drawn. So that would be a stereogenic center, and this one right here would also be. So I know right away that I'm going to have 2 to the 2 or 4 isomers. So I need to be able to draw 4 stereoisomers. Stereoisomers. So when we get into meso compounds here in a little bit, we're going to learn that we actually have to kind of flip these things down so we can see them a little better. And I'm just going to go ahead and do it real quick so we can get used to it, and then we'll draw the stereoisomers from there because it'll be a little more fun. Because oftentimes we're going to look to see if we can make something that's a mirror image, and we're going to make like a bridge. So first I'm going to take this right here, that bond right there. So let's go ahead and label the carbons. This is 1, 2, 3, 4, 5, 6. So between 3 and 4, I'm going to draw it like this. So that's my 3 and 4. That means I need a 3 going to a 2 and then a 1. So 2 and 1. So this would be like my 1, 2, 3, and then 4, 5, 6, 4, 5, 6. I don't know, kind of like the little shrugging dude in your iPhone in the emojis. Is kind of what this reminds me of, like, I don't know. So anytime you have something that's got one that's going up and one that's going down like this, we're going to flip it so we can see it a little better this way. So essentially all we did was just kind of rotate the bond here like that. Okay, move this chlorine down, and then we drew it this way. Okay, so on this number 3 we had a chlorine, and on the 4 we had an OH. So I like almost always starting with the wedges. I don't know why, it's just a habit I got into, so I'd say we just stick with it. Okay, so that's 1 stereoisomer. Yay, we're almost there. All right, as you can imagine, I think the other one would be if we do dashes. Cool. Another one, we draw the shruggy dude or dudette. Let's do 1 wedge for the chlorine and 1 dash for the OH, and then 1 final one, 1 dash for the chlorine and a wedge for the OH. When you draw it like this, it just makes it a little easier to kind of pay attention to things. And again, we'll eventually be looking at situations where we look to see if there's a mirror image on either side. So it's good to just get in the habit of, when you see something like this, twist it around, draw it like this, and it'll make it easier to see. Okay, so those are the 1, 2, 3, 4 different stereoisomers of this compound. just realized it again. I'm using a pen, not a marker, I'm sorry. Okay, so there are only two types of stereoisomers. Enantiomers. Enantiomers are the mirror images, like we just drew right here. So this and these two things would be enantiomers. These are mirror images of one another. If you remember, we could have also drawn the mirror image, or you just flip all the wedges to dashes, and that will give you the enantiomer. These, however, this is the diastereomer with this. This is the diastereomer with that. This is a diastereomer with this, and this is a diastereomer with that. So like these are diastereomers. They're all non-superimposable things. But a quick way to look at it is if one is like cis and the other one's trans. Is probably the best way to look at whether things are diastereomers. So here we have something that is cis, and over here it is trans. So those would be diastereomers. They are not mirror images. Okay, so it breaks it down even more over here. It draws it kind of the way that we talked about, which is what you'll see a lot, kind of the bridge or the shrug in person. In this case, I don't know, it looks like a dog to me, like that's its little tail and that's its head, and it should have like a little tongue sticking out, and its tail is wagging. Oh, it's a happy puppy, yay. Okay, that I don't know if you saw that or not, but makes me happy. Okay, so this image over here and this compound over here is a mirror image of this compound over here. We could have drawn the same thing just by, again, instead of drawing the mirror image, we could have put the bromine on a wedge, and then the hydrogen would naturally have been on a dash. We don't really have to always draw the hydrogen. So these are enantiomers. These are enantiomers, but this and this are diastereomers, and this and that are diastereomers. So, and it kind of walks you through those things. So A and C are diastereomers, A and D are diastereomers, B and C are diastereomers, and B and D are diastereomers. So if they're not mirror images of each other, then they're going to be a diastereomer. Another quick way to look at that again, if you've got something that's cis versus something that's trans, those would also be diastereomers. All right, we're going to talk about a meso compound. So meso compound is an achiral compound. I don't know if you remember when in the last lecture there was a brief mention of sometimes you'll have something that has stereogenic centers, but it's not chiral, meaning it's still superimposable on itself. And the way we get that is if we have something that has a mirror image of itself. Okay, so let me give you an example. So it says draw a meso compound for the following molecules. Okay, so let's go ahead and draw this. Anytime we have this bond, we're going up, down, and down. We have one thing up, one thing down. Let's go ahead and draw this as our little shrugging person. So however you want to draw it, 1, 2, 3, 4, 5, 6. So I've got 6 carbons. Okay, this is a hexane. And I know that the bond between carbons 3 and 4, I'm going to draw like this. You can go up, you can go down, you can do whatever you want. I'm going to go down. So this is now my 1, 2, 3, 4, 5, 6. And this is going to take practice. It's definitely you're going to have to do them a few times before you really start to get the hang of it, but it really does help to label those carbons, find out which one you're going to draw horizontally, and then go from there. Okay, on the 1 I had a bromine, and on the 6 I had a bromine. And I don't know if you can see what I'm trying to do here, but I'm trying to see if there's a mirror image in this thing, because if you can draw a compound with a chiral center that happens to have a mirror image, you've drawn a meso compound. Okay, chlorine is here on number 4. I'm going to go ahead and put that sucker on a wedge. And I'm also going to put this one on a wedge. So as you can see, the compound itself has a mirror image built in. So A and B are mirror images of themselves, and anytime you have that, that's called a meso compound, meaning they are superimposable on themselves. So you could take this compound, you could do its mirror image, and you could flip them around and they would still be the same thing. So it's not like our hands, right? It'd be if our hands had a mirror image and this was all of a sudden my ring finger and this was the thumb, then that would be the example of a meso compound. All right, now we got this one. So same exact thing. This one already, you can see the natural mirror image in it, so we don't have to do it like this, because I could just draw a plane of symmetry right there, right? And I can see that the stuff on the left is equal to the stuff on the right. So when drawing a meso compound, you just want to, let me do this. You just want to make sure that the things that you're drawing are going to be a mirror image. I was going to write CH3, but I didn't, so I'll just draw it like this. So that would be a CH3, and that wedge would be a CH3, and this would be my plane of symmetry. I could have drawn them as dashes as well. If I'd drawn one as a wedge and one as a dash, it would not have been a meso compound. Okay, so again, these are meso compounds. They have stereogenic centers. But they are not chiral, meaning they are still superimposable, might be a way to. So you can still turn this one around and get the mirror image. So if I drew a mirror image of this one, I'd get back the exact same thing. And if I drew a mirror image of this one, I'd get back the exact same thing. That would be superimposable, and you'd have essentially the same molecule. Okay, so here's a brief summary of it all. We have isomers, right? We talked about constitutional isomers. Constitutional isomers would be if this bromine was maybe if this bromine right here was maybe up here instead, right? That would be a constitutional isomer. So when isomers, or when atoms are bonded to different atoms in a different way, that's a constitutional isomer. Stereoisomers are isomers that have a different three-dimensional arrangement, right? They're still bonded to the right atoms, but maybe one's pointed up and one's pointed down. Those come in two different ways. One would be an enantiomer, which is a mirror image, and the other one's a diastereomer, which is not a mirror image. In enantiomers, remember, if one is R, the other one will be S. But in a diastereomer, this is going to be the difference with like cis versus trans. So let's use that information to see if just by the naming here, we can figure it out. We don't have to know a lot about the naming in this situation, other than that we're looking at the R's and the S's. So what this is saying is the second carbon is R in this one. And it says label each pair as enantiomers or diastereomers. Okay, so in this one, the second carbon has an R, and we're comparing it to this one, which also has a second carbon, R. This one has a third carbon, S, and this one has a third carbon, R. So those two switched, but that one didn't. That means this to me looks like it's going to be a cis-trans situation. These are diastereomers. To do a better job, if every R switches to S and vice versa, that's when you'll get an enantiomer. If just one switches, that's when you have a diastereomer. So that's what happened here. This 3 switched, but 2 didn't, and so we had a diastereomer. Here we have a 2 that was an R, and we're comparing it to the structure that has a 2 that's an S. So that one switched. Here we have a 3 that's an R, and a 3 that's an S. So that one switched too. So cool. So both of those switched. It went from R and R to S and S. This must be an enantiomer. In other words, they went here, maybe something was on wedges over here, now it's on dashes over here. All right, let's look at this one. Here we had an R that switched to an S, 2R to a 2S, that's good. Here we had a 3S to a 3R, okay, that switched, but there's a 4R and a 4R, that one didn't switch. These must therefore be diastereomers. All right, next it says state how each pair is related. If they are enantiomers, diastereomers, identical or not. All right, one of the better ways is to, if it doesn't come intuitively to you and you don't want to like flip things around in your mind, it can be kind of difficult and it's easy to make mistakes, is just label them as R and S and then see what you get from there. So for example, here's, if we label these, this one's 1 in terms of priority, right? My oxygen's 2 and this thing is 3, and I'm looking at that stereo center right there. So 1 to 2 to 3 goes like this. The H is in the back, right? So this one would be an S. Looking at this one, my center's right here. My priority is 1, then 2, then 3. Goes from here to here to here. This is also an S. This chiral center right here, both of them have this ethanol group, a bromine and a methyl. It's got an ethanol, a bromine, and a methyl. They're both S configuration. These are actually identical. Over here, we have one that, two very similar looking things. One's on a wedge and one's on a dash. And that tells me immediately these are mirror images, right? Remember the two ways we can do mirror images is one by drawing a mirror and the other by just switching the wedges to a dash. So this would be an enantiomer. Okay, over here, I might go to look at it and say, oh, look, this one's cis and this one's trans, but then I realize these aren't even on the same carbons, right? This is on carbon 1, 2, 3, 4. This is on carbon 1 and 4, and this is on carbon 1 and 3. So these are two totally different compounds. These are constitutional isomers. Okay. And then we get to here. Remember, if they were enantiomers, we'd switch them both. So these would both be wedge. These would both be. This would be a wedge, and that would be a dash. But that's not the case. We only switched one of them, and because of that, this would be a diastereomer. Much like up here, where you might switch one or two, but not all of them. It's still a diastereomer. Ooh, Jurassic Park. Let's talk about it. All right, so I don't know why this came to mind. I was just trying to think of like a way to explain this, but we're gonna talk about polarized light here. So in Jurassic Park, if you've ever seen the beginning of the movie, or I don't know, it might not be the beginning, but somewhere in there, somebody's looking into a glass. So imagine looking at the top of a cup of water, and there's something nearby that's like making it vibrate, boom, boom. You see these little ripples, right, in the water. They ripple out like that, okay? So imagine if you put a grate in that water, like something like this. You're gonna see it like a cow grate or something like that, and you put that in the water. What would happen is, if you put your grate right here, so imagine you put it down into there. What would happen is the light would go, or the waves would go boom, 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 boom. They'd align. Instead of going all different directions, and they boom, 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 like that. So they line up. What you would do is you would polarize them. You'd make them all be in one specific direction by putting a grate in the water. So if something goes in pounds, all the little waves in the water go in the same direction. All right, so Normally that's what happens with light too. You've probably seen polarized glasses. Maybe you've done the test where you put on polarized glasses and you can see the fish in some kind of weird image. Essentially what it does is it gets rid of all the directions, and it changes light so through a grid so it's only going in one direction. It's called plane polarized light because it's only going in one plane. All right, don't forget that light acts in waves, right? So it's very similar to this. Okay, so an achiral compound, if you have something that's achiral, or we will call it optically inactive. And that's because if you run it through a polarizer, you should throw light, you run it through the grate, you expect it to go in these directions, and that's exactly what happens. It runs through in a plane. So there's no change whatsoever. So that's with achiral compounds. So that could be with like a meso compound that we talked about. Meso compounds, remember, they're mirror images, but they're achiral. Or it can be with any other achiral compound. It won't do anything to it. However, if you have a chiral compound, non-superimposable on itself, right? Then, like your hands, with a chiral compound, when you run light through it, through a polarizer, and you have a sample of that chiral compound here, it will actually shift the direction of the light, either clockwise or counterclockwise, and to a certain degree, to a certain extent. Sometimes it'll be really shifted, and sometimes just a little bit shifted, and it's measured in terms of degrees. Okay, and then we can analyze the light coming out and realize, hey, this light flipped. So that's what chiral compounds do. Okay, if the rotation of the chiral compound is clockwise, then the compound, it's dextrorotary. So it's a rotation that's, we label either D or positive. Mostly positive is what most people stick to until you talk about drugs. And oftentimes you'll see drugs labeled as D or L in the pharmaceutical industry. Okay, so if something's, it rotates clockwise, we call it positive. And you know how I already told you clocks are right? Remember, if something goes clocks are, I can spell clock sometimes. Clocks are right. That's for the R configuration. Now clocks are also positive. So if that helps. But be careful because I just kind of did you a disservice. I'm just helping you remember that clockwise is right. But R does not give off positive. Those two things are actually completely unrelated. Positive and negative have nothing to do with R and S configurations. So again, if something rotates clockwise, it's going to be R if you're talking about a compound and the priorities. If light rotates clockwise, it's going to be positive. I'm going to shut my door here. Okay, but it has nothing to do with the fact that it's an R or an S configuration if it's positive or negative. The only way you can do that is running through a polarimeter, which we have in lab, and maybe I'll come up with a lab that we can do, and that will tell you what it is. Otherwise, you can't tell. Okay. If you have a 50-50 mixture of two optically active compounds, so maybe one that's rotating light to the right and one that's rotating light to the left, you're going to have what's called a racemic mixture, and those will be optically inactive, okay? So if you have a compound, maybe that one goes to the right, one goes to the left, as long as they're 50-50 amounts, they cancel each other out and they're optically inactive. All right, so let's put this in terms of actual compounds. Okay. So when you have two enantiomers, generally their physical properties are completely identical, especially with their interactions with different chiral substances. So, or except, thanks. I was like, oh my goodness, that doesn't make any sense. Yeah, except in their interactions with chiral substances. So for example, if you have something that's just chiral, just one compound, and it's chiral, and then you have the other compound, like let's say you have one R and one S over here, their melting points are actually going to be completely identical. Okay, so any two enantiomers. So like let's look at A and B. These two boiling points would be completely identical. All right, but if you have a mix of them, their boiling point actually might be different from if they were purely alone. Their boiling point, the same exact thing. This boiling point is the same as that boiling point, but if you mix them together, you're going to get a different boiling point. And in terms of optical rotation, remember we talked about, we can't tell if one's R or S, if it's going to be positive or negative. But for example, this chiral compound would be optically active. This compound would be optically active. And then a mix of these two, if we had 50-50 mix, assuming they're optically active in opposite directions, they will cancel each other out, and you'll have a racemic mixture, and you'll have no optical rotation. They'll be inactive, and they won't polarize, they won't change the way the light goes. Okay, so let's look at these questions, even though I just kind of went through them, and write it down. So make sure that you're completely in agreement and understanding this stuff. Okay, so it says, how do boiling points of A and B compare? So for A, we know that A must equal B, right? The boiling points of this and this must equal. These, by the way, as you can see, are mirror images of each other, right? These are enantiomers. As opposed to these, A and C and B and C are diastereomers. Okay, so A and B are equal to each other, but diastereomers are completely different. A is not equal to C, and B would not be equal to C either, even though I didn't ask that. Okay, so in terms of boiling point, melting point, these two would be identical, these two would be different, these two would be different. Okay, it says, what about optically inactive or active? So A, we would consider it as active. Again, that's because it's a chiral compound. B, active, also a chiral compound. C, this would be inactive. This is an achiral compound. D, if we mix these two together and we have 50-50 mixtures, this would be inactive because A and B cancel. Okay, and E, if we have A and C, and we mix those together, although C is inactive, A would take precedence, and this would be optically active. So it would rotate light. Again, that's because A drives the activity. All right, so yeah, I hope that kind of helps. Again, C would be optically inactive because this compound has a mirror image in it, right? This is a Meso compound, just to point that out. So even though it has two stereogenic centers, it's superimposable on itself. So this is achiral. And I realized I probably should have pointed that out earlier. I'm sorry I didn't, but hopefully that helps. And these two are chiral. So, all right. I think is that it for today? I think that's it for today. Woohoo! We rock that. All right, guys, have a great week, and I will see you soon.